you're dealing with the arithmetic stuff, that means that there was a common difference between each number. You were adding or subtracting between all your terms in the sequences. Now, when you're talking about geometric, you're multiplying or dividing within that. So you could be multiplying by 2, you could be multiplying by -6, you could be dividing by 4, you could be dividing by -33. What happens is you have this common ratio now between the two. So yesterday we had this common difference, we used the letter D. Today we'll have this common ratio, and we'll use the letter? All right.
All right.
So,
All right.
Oh, God.
Look at the right arm angle.
it's like it's rolling, saying it.
Where was this one?
The newspaper.
It was? I thought it was.
No, Izzy was in there twice. She's twice as cool as you. What's that?
Caleb Mom.
Anywho, like I said, in a geometric sequence, there's a common ratio. What's that? There's a common ratio. And this formula is going to be also very, very, very easy to work with. We're going to look to divide. And in order to figure out these common ratios, we're going to follow this exact same pattern each and every time. Here's what happens. When we look at two sequences, we want to tell whether or not they're geometric. That means there has to be a common ratio between the two. Ratios, remember, is a comparison of two numbers by what? What? Very good. A ratio is a comparison of two numbers by division. So what you do here is, and this works every time, you take the second term divided by the first. You take the third term divided by the second. Fourth divided by third, and so on. And you're checking to see if those ratios are all the same. Well, does 2 equal 3? No. Does 3 equal 4?
No.
Does 4 equal 5? Are these ratios the same? Is that sequence geometric? No, it's not. But could you probably figure out the next terms within that sequence? Yeah. You could. I mean, that's one of those things you guys were working on in section 11.1, just trying to find the pattern and identify, could you write it out? Now, I'm not going to make you write out these types of rules or anything like that. What we're doing is just trying to identify if you do happen to have that geometric series or sequence. Remember, the series is just the sequence with addition symbols. Look at part B then. If I follow that exact same pattern, bless you, take the second term of the sequence divided by the first. Does that equal third divided by second? Does that equal fourth divided by third? Does that equal fifth divided by fourth?
Yeah.
Those all have the same common ratio. Do you agree? What is that common ratio? 1/3. The common ratio here is 1/3. In order to get to the next term within that sequence,
I did first divided by the second.
remember, always go with that pattern of get a step ahead of yourself. Remember that. Be a step ahead. Bless you. Always work the second to the first, third to the second, okay? Always work a step ahead. That's what we're looking to be able to do. So once you're able to do that, you can then work with the generic form for the nth term. And that's where that's where we're going to start with. The nth term for these is always the first term times your rate to the n minus 1. I'm sorry, times the ratio. Again, working with these ratios, once you identify the ratio, it is relatively easy. The math that we're going to be working on here today, again, not going to be tough. It's basically a lot of calculator stuff, but it's not, they're very user-friendly formulas.
Are you multiplying?
Yes, yeah, I'm going to show you what it looks like when we write out the nth term for this sequence. For this sequence, again, we identify what our first term is. What is it? 81. And do you remember what the ratio was? 1/3. So when you go to write out this in terms of the nth term, it will always look like the following. First term times your ratio, excuse me. Put that in parentheses to the n minus 1. And that's it. That's all it is. Believe it or not, you've worked with this problem before. We worked with this when we started talking about logs and exponents. We graphed these, e to the x, that kind of stuff. You graphed these problems before. Exponential growth, exponential gain. Yes, no.
Is that because
Yeah.
we went back in time again?
Yes, we're gonna go back in time.
Well, I mean, like, was that a later chapter?
No, that was chapter 8.
I
So
don't-
it's in a previous chapter that we did have to go back in time to. Wow, this whole space-time continuum thing is getting kind of weird.
Yeah.
It's a good thing 88 applies.
Or is it the flag?
So let's write the rule. Let's write the rule, and then let's figure out how much, what is the 8th term in the sequence. So our sequence goes -8, -12, -18, -27. Start by writing it out. What do all of those simplify to? 3/2. Very good. And what was the first term within the sequence? -8. So our rule would be -8 times 3/2 to the n minus 1. And again, if all I want to do is figure out what the 8th term is, what do I substitute in for n? 8. So the 8th term will be -8. And what did you guys get?
Something ugly.
What's that?
Something ugly.
Math enter, get the fraction.
Yeah, it was a fraction, it was just really ugly fraction. Negative 2,187 over 16.
2,187.
87.
Thank you.
Yeah,
That's fine. It's an ugly number.
I don't like it.
All numbers look the same to me.
They're all pretty and happy.
Some fantastic numbers.
All right, I apologize.
That's just not good branch.
Yeah, always go that way. Always go second over first, third over second. Work ahead. Always get ahead of yourself.
Yeah, I
That's
did
the
the
easiest way to set those things up.
up.
Not so bad, is it?
Can't you just take a second channel of the first and then second?
You can. You can do that if they say write the term for this geometric sequence, because they're telling you that it already will be a geometric. But sometimes it might not be known that it is geometric to start with, like the first two examples we looked at. So you might have to check it first. So if it says this is the geometric, write the rule, yeah, absolutely, just do it once and be done. There's no reason not to.
But then if you have to check what the question be like, is this in arithmetic?
Yeah, it might be write the rule for either the arithmetic or the geometric, so you might have to check between the two. That's all it is. And we'll mix them up in a little bit. So just like yesterday, when we got from the generic rule with the difference here, then we jumped into, all right, well, the 5th term had a difference of 6. What was the, write out the rule? We'll do the same thing. Do you want to write out another one on your own?
Yeah.
Not really.
All right, well, let's go to this then. We'll do the same idea. Let's say that we have the 3rd term of a geometric sequence is 5, and the common ratio is 2. Don't worry about graphing. We're not doing that. We already have. There's no point. So just like yesterday, we're going to kind of rewrite this formula out a few times, just so we get this kind of committed to memory. First term, rate to the n minus 1. If I'm working with the third term is the first term times the rate to the 3 minus 1. Well, that means 5 equals first term times 2 squared. Just by filling in the blanks. What's 2 squared? How do I get the first term by itself then? Divide by 4. So what's your first term? So there's your first term. And your rate, I believe, was 2 to start with. Therefore, when we go to write our rule will be our first term times the rate to the n minus 1. This is nothing more than a lot of substitution back into the generic formula and working your way out of it. Okay. Well, when it gets weird then. Just like yesterday. When it got a little bit weird is when you had to write out a system of equations. You had to put two things together to figure out the generic. We can do the exact same thing with the geometric stuff. Personally, I think the geometric stuff is a little bit easier to work with than the arithmetic. The reason is, here you have to do the distributive property and then combine like terms. A lot of times you guys will miss a sign. You'll do a negative times a negative and all of a sudden it's a negative and you'll add it and all of a sudden it becomes positive and bad things happen. Whereas with geometric, you're just multiplying. There's not a lot of weirdness that happens there, okay? So we're going to do the same process as what we just did. We start out with the generic formula, a sub n, your first term, rate, n minus 1. And I'm going to write it all out in terms of the second term. So the second term is the first term times the rate to the 2 minus 1. So 45 equals first term times r. Because 2 minus 1 is 1. Okay with that? Do the exact same substitution style steps when you have the fifth term being negative 1215. The fifth term is the first term to the r 5 minus 1. So negative 1215, first term r to the fourth. So at this point, you've got these two formulas. Two variables, two equations. There's no addition or subtraction here, so I can't combine them. But can I set one of them, use substitution somehow, you think? This is the only thing that I will say that you always, always, always will do with these. When you have systems like this, you will always take the first, get that by itself. Always get your first term by itself in one of the equations. How do I get the first term by itself in this equation? Good. Divide both sides by r. So that way 45 over r is the first term. Because now what can I do in the second equation? Are you doing it extra work?
As a strike, you can use that.
Shocking, isn't it?
That's like
You get your strike.
Thank you. So you're going to substitute
Count things at the end of the day.
into there. When you substitute back in, you get negative 1215 is 45 r to the fourth over r. What do you get? Yeah, exactly. You'll wind up dropping some of the degrees off to one side here. So you get negative 1215 is 45 r cubed. And now it's a two-step equation to get r by itself. What do you have to do first? Divided by 45? What is it?
Negative 27.
Negative 3. The cube root of a negative value will be negative. You guys remember where the cube root button is on your calculators? Yeah, so negative 3 is your r value. Well, all we've done now is just found out the r value. We still have to write out the rule. What's your first term? Well, I know my r value is negative 3. I substitute back in there. You get negative 15. Very good. So this is where making sure you can keep track of your writing in some sort of an order to help you put this all together. Here's your first term, and there's your r, the rule.
Why is it negative?
What's that?
Why is it negative?
Why is what negative?
45 divided by negative.
45 divided by negative 3.
Where's that?
What's that?
Where's the
Math. Hit math and scroll down. Cube root button in there.
math
There's also, you might have to do x roots, so you might have to mess around with that one. So do the same basic idea with this one, and write out the rule. Well, I don't want to overstep my bounds. We got time, so it's not a big deal. Again, always start these problems out with the generic rule.
Don't do it again, Murder. Yeah, Murder. Don't do that.
Oh, okay. I thought you guys were done.
It's a lot.
So again, all you gotta do is fill in the blanks. Second term, first term to the r, 2 minus 1, negative 4. Same thing. When you divide it out, you probably forgot to bring the negative over.
No, I did.
Well, what's a negative divided by negative?
Oh.
Fourth rooted, what is it, 6? No, it's 4. 4 is r. Your first term is negative 1. So your rule. This stuff does get nasty. It does get a little bit weird when you have to find the summation, the sum of the series of these things. I can't fly through that in 5 minutes, so we'll stop. What I want you to do here tonight. Wait, what? So that's it. The generic rule will be a sub n.
Gosh,
Should I sign?
no, but for a, instead of a squared and putting a or 2 up on for n, I put negative 4.
That's what I did too, then I got like.
And then my hours canceled out and stuff. It was messy.
Oh, yeah. Don't do that. At least you caught it.
Yeah.
All right. So what I want you to do tonight, it's what, 11, section 11.3, it's page 670, numbers 39 through 53. I had to think about which ones they were. Can't imagine this should take you very long. Do all of those, please. I think it's 14 problems. All right. We'll get into the weirder stuff of the summation of these tomorrow, and we'll mix them together with the arithmetic and see if you guys can figure out which one's which. All right.